Hello, my friends. Bradley J here, and it's the Bradcast. We're with Doug Arion, who's a physicist, an astronomer, and a teacher, and much more. And the reason he's here is to teach us the basics of what quantum computing is. I hear about quantum computing, which is going to make regular computing, I guess, my laptop, obsolete. And I need to find out how far along this is. I need to find out what it is, how it works, how it's going to affect the future. So that's why Doug is here. Hi, Doug.
Hey, Bradley. Great to be with you again. A lot of fun.
In the beginning of the pandemic, I somehow fell into the trap of deciding to learn about quantum physics, quantum mechanics. I learned a lot, and it's important. As a result, I know it's important to understand a few of the basics, the very basics of these concepts before we get into quantum computing. So we're going to blow right through that. Do not be intimidated. Just glean what you can. Doug's a teacher. He knows how to impart these principles to people who are probably younger than you, and it's going to be fun. So here we go. Quantum computing. Quantum computing comes from quantum or quanta, and right at the base of it, I think it's important to explain what quanta are or what a quantum is. And as I understand it, a quanta is a little packet of energy, which is the minimal energy it takes to boost an electron one level or higher around a nucleus. And also, if it loses, it gives off the same amount of energy when it drops back down. Am I basically correct? And how does that fit in?
So you're right. The term was first developed to talk about light and interacting with atoms. And one of the fundamental things that was discovered is that when you look at things that are very small, things like atoms, everything happens in little steps. Things aren't continuous anymore. So you can talk about, how much water you're putting into your coffee, and you can put in an ounce or 2 ounces or 3 ounces or 1.1 or 1. Any amount, right? But if it was a quantum coffee cup and you tried to fill it, you would get 1 shot or 2 shots or 3 shots or 4 shots, right? Just these single blocks of things. So it turns out that when you get down to things like atoms, everything about an atom comes in steps.
Okay.
And have any value you want, you can only have these steps. And that's really weird, but that's what they do. And that's a big part of what makes all of these other things happen.
Okay, then what is quantum physics, now that we understand what quantum means?
So quantum physics is understanding what happens when things are very small and energies are low and temperatures are low. Any of those things mean we're now talking about very small things, very tiny amounts of energy. And each of those things works in these little itty bitty little steps. And that also means that everything only works on the basis of probabilities. Okay, so this is a really bizarre aspect of quantum physics, that when you start looking at individual atoms or molecules or things that happen on the small scale, all you can know about is the probability of something happening. And that's going to be a very big part when we start talking about quantum computing. So if there's an atom here, let's say there's an atom right there, and it's doing its thing. When I go to measure it, I bounce light off of it or I study it, the electron, as you said, will be in one level or another level. But while I'm not looking at it, the electron can be doing whatever it wants to do. And I can only calculate, I can only determine how likely it is to be in that upper state or that lower state. Then when I look at it, either the light comes out or the light goes in, I know whether it was going up to down or down to up. But I can't tell that beforehand.
So you can never really know where a particle is. You can only guess the likelihood of where it is. You can never really tell where a particle is. You can only guess the likelihood of where it's probably.
Exactly.
Okay,
now you can,
and then there's go ahead.
No, so you can get close, right? You can make, get better and better and better with those probabilities, but you can never know for sure.
How is quantum physics the same or different than quantum mechanics? Is that the same thing?
They're the same thing. Yeah, different name for the same field.
Now here's the weird one. Quantum entanglement. What is that? Folks, hang on to your hat for this one. Quantum entanglement is the coolest thing. If it's real, and it's been shown to be real to some degree. Go ahead.
So here's the thing. Because of the way that particles work, they have to essentially communicate with each other. So, for example, we take a simple atom that has two electrons, like helium. Those two electrons have to sort of be in opposite states. You just can't put two of the same thing in the same place at the same time. They have to be opposite in some way, what we call spin. And here's the thing. If you take that and then you take those particles and you move them very, very far apart, and you mess with one of them, the other one knows that you messed with it because they were once together, so they know to communicate, they know they're brother and sister. You separate them. As soon as you mess with one of them, the other one responds.
Okay, couple questions. How do they get paired? You touched upon that. How do they get entangled? How do they get paired? What are some things that happen to entangle particles?
They need to be essentially close together on an atomic scale so that their properties can interact with each other. So you can, use a laser that produces pulses of light, and as that pulse of light gets generated, those pulses are coming together, right? Or I take the electrons that have been interacting in an atom, or I have atoms that are very close to each other. And that's one reason when we get to quantum computing, things have to be very cold, right? Things have to be very close together and not moving a lot so that these interactions can happen.
And here's the super weird part. Once the particles are paired, even if you move one 10 million miles from the other one or more, when something happens to one, it affects its partner instantly, no travel time, instantly, correct?
That's what we think. Einstein was not happy with that. Calls it spooky action at a distance, right? It seems like magic. And let's put it this way. We know this stuff happens. It's not well understood. This isn't just like, I don't understand it. It's like, it is not understood yet. There are folks who are trying to understand it, but it definitely happens.
So the weird part about that is if it's a million miles away and happens instantly, there's no travel time. And the maximum, as far as folks know now, that anything can travel at the speed of light, which I doubt. I think they'll find that's not true later on. But even so, instantly, there obviously, if the change happens instantly, if there's spooky action at a distance, there's big chunks of stuff that we don't know. But
Right.
we can't go too deeply into that because we're trying to figure out about quantum computing. Now, 1993, a paper was written about the idea of quantum teleportation. Is this similar to what we're talking about?
Yeah, very similar to what we're talking about, being able to transmit information and connect things from one place to another. Yep.
Okay, and in 2004, there was a 5-photon entanglement demonstrated. So it's not just one paired with one. There are multiple pairings. Can one affect 5, or does it have to be 5 affecting 5, or we don't know?
Well, each of them is connected to the other. And so, yes, as you mess with one aspect, the others respond to it. Right.
All right.
And when we get to quantum computing, that's one of the goals, right? Because if I have one particle, I know its property is either up or down, right? There are 2 states to it, or left or right.
Mm-hmm.
But if I have 2, there are 4 possible combinations, right? This one can be up or down. This one can be up or down. If I have 3, there are 8 combinations. If I have 10, there are 1,000 combinations.
Okay.
If I have 100, we're up to millions and millions and millions of combinations.
So I'm guessing that's what makes quantum computing faster, because in a regular computer, everything is based on ones and zeros, on or off, one thing at a time. But if you can pair multiple particles or multiple units, then that would exponentially speed things up. Is that kind of the reason that it's faster?
That's exactly right. So it's a capability of doing many, many things essentially at the same time. So there are a lot of problems where you want to interrogate many possible combinations at once. If you use a regular computer like your phone or your laptop, it has to look at each one at a time, right? If you said, what's the best order of doing something? It says, well, let's test this order and see how it goes. Let's test this order, see how it goes. Let's test this order and see how it goes. And it'll run through all of them. But that takes a long time, right? How about a machine that could say, I'm going to look at all of these at one time and tell you which the best one is? And that's what a quantum computer can do.
So it goes
Really
beyond,
fun.
almost beyond comprehension how fast this could be. Now,
Yep.
here's the next step. It's tough for me to visualize. I see my laptop. I kind of get how it works. Would there actually be hardware, with a quantum computer at some point that you stuff in a box that you buy and it works in your home? And what would be in the guts of it?
Well, we're a long way from having one that you can put in your home. Right now, they're in very large stainless vacuum chambers in laboratories with a lot of equipment around them to make them work. But to make you feel better about that, think about what computers were like, say, in 1935, 1940, right? Early computers in World War II. If you saw the movie The Imitation Game,
Yeah.
about the first computer to break codes. And we're going to get into that because that's one of the most powerful things that a quantum computer can do is breaking encryption. So we'll talk about that in a second. Think of that huge room of equipment, and it took hours to crunch through each individual calculation. But that was a huge revolution, right? It could do something that you couldn't do by hand practically. When you think about the first calculator you got, the first calculators were the size of typewriters, and all they could do is add, subtract, multiply, and divide. Now you have a gizmo in your pocket, which has way more power than the supercomputers of 30 years ago, which can do 3D everything right on your phone, right? You can do 3D models of stuff and talk to people and transmit and do all this stuff, and it's now little. So what will happen over time is it'll start as a big laboratory object, like that computer and Imitation Game, and then it'll become something like what a mini computer was. A company can have one to do some problems, and it will evolve, right? It will evolve and do things. But there are going to be some limits to the physics as to what you can do. But the goal is obviously to put one on chip. Eventually, you have a chip that has the same physics going on in there. But that's down the road a ways. I don't know if you and I will see it while we still are young enough to play with it, but it'll get there.
So I should not hold off on getting a new computer, waiting for a quantum computer. I should just go ahead and get a new Mac.
Yeah, get a new Mac.
All right. I can't help but think of the 80s movies where when they had computers, they were big boxes, big kind of off-white boxes with just text on the screen, green text.
Yeah.
It's kind of like the difference between Pong and a current generation video game.
Oh yeah, absolutely, absolutely. And we were so excited to have those computers that had that little screen with the little lettering on it because we could do problems we couldn't do before. I got an early personal computer to help do my dissertation research because it was expensive. It was $3,000 to buy that in 19.
Wow.
What year would that have been? 83? Think about how much money that was, but it lets you solve a problem. And now that thing is, it's long gone, but it will be a doorstop. It can't do anything today compared to what your phone can do.
Okay, the next thing I do want to address it because I want to understand it. If you can tell me about it, is that one of the roadblocks is fault tolerance and a related thing called a noisy intermediate scale quantum machine.
Yeah.
Can you talk about the problems with fault tolerance and what that means?
Sure. So fundamentally, a quantum computer has a collection of atoms or particles that are trapped together that you manipulate. It's similar in your current computer where you manipulate the transistors to be in a certain condition and then you do some math with them to find out what your answer is. Here you put some atoms in a certain configuration and they interact with each other and then you read out that configuration when you're done and that gives you your answer. That's simplified, but that's basically how it works. But to make that happen, all those atoms can't communicate with anything else, right? If you get any little tweak in there, you have, an error, right? It's not doing it perfectly.
Right.
So it's very hard to do that. And that's one thing. The second thing is, remember, these are all probability machines. That it gives you the most likely answer out of something. And there's a distribution, right? Most likely doesn't mean it's exact, it's close. So the trick is you need to develop technologies and techniques to minimize those problems, to have error correction. So for example, the internet uses error correction right now. When you send a pulse of information, what you and I are doing right now, we're sending tons of information back and forth over fibers, right? The image on our screens is being transmitted, our voice is being transmitted. Those packets of information can accumulate little electrical errors as they go along, but there are little bits of key that go along with it that say, oh, make sure that this is right before you read it or you can correct it. One way to do that is just add up all the numbers in your collection of information and send that sum with you. And if you get that information and it doesn't match the sum, you send that to me again. I wasn't sure about that. It's like checking your checking account against the bank statement, right? You go, well, is the total the same? Total's different. Let me go back and find out where the mistake is. So there are ways of doing it, but in a quantum computer, it's more complicated because it's a probability machine. So you have to work with ways to do that. So that's why they say fault tolerant, not fault proof, but fault tolerant. How do we make it resistant to doing these things?
So you need to get it so the result approximates what you started out with so that it's usable.
That's exactly right. So when you think about it, even a spacecraft, every spacecraft, like the shuttle had 3 computers, all doing the exact same thing, and it would vote on everything. At least 2 of those computers had to say the same thing to be sure that you had the right thing, to make sure that one of them didn't hiccup.
Right.
Error correction.
Okay, so now I think we get into the interesting part. We can spend a lot of time on this, and you can go into detail on applications. What can you do better when you have a crazy faster computer? I know. Go ahead. You take it away. Go ahead.
So imagine that you're the United Parcel Service, you're UPS, and you have all of these packages that have to get from point A to point B as quickly as possible, and you want to use as little gas as possible, right? And you want to use the most efficient transportation, whether it's airplane or boat or truck. And you have to lay out all those routes. And it's heavily constrained because flights can only take off at certain times and land at certain times. And then there are roads. There are roads that are faster. There are roads that are slower. There are roads that have traffic at certain times. Imagine you had to lay that out. That would be very, very complicated. So with your conventional computer, you'd put in, here are all the packages that I have, where they are, and here's where they all have to go. Now look at every possible way that each package could get to its destination by all the possible routes, and then tell me the best way to do that. And that's hard to do, right? I mean, think of how many different routes are there between San Francisco and Orlando? How many different roads could you drive on? How many different airports could you use? Now imagine a quantum computer that had enough computing power that, and we're not there yet, right? We've only gotten up to a handful of particles together, but not far down the road, when you have hundreds of these particles talking that can look at literally trillions of combinations at once, imagine that it had the roadmap of the United States. And you said, here are my packages, here's where they need to go, what's the best route? And in a matter of seconds, it laid it all out for you.
Yeah, not only the best route, but then the best time, the best type of vehicle among your fleet, which drivers would be best. That is amazing. And of course, it does this for thousands and millions of packages at the same time at once.
That's right. So imagine that in a matter of a few hours, you could diagnose all that. So all the packages get picked up at 5 o'clock. That's roughly when your box is closed, right? All this information has been scanned in. They're all read in. The computer looks at it. Imagine if by 7 o'clock, every package knows where it's going, how it's going to go there, and the vehicles go. And by doing this, so your shipments go faster. That'll make your customers happy. But imagine that you could cut down on your vehicle cost and your air cost and your labor cost. There's a huge advantage to doing that. So any kind of problem you can imagine where you have many combinations that you need to look at, that's where a quantum computer is going to be better than a digital computer. For lots of other things, a digital computer is still going to be better. This is not one taking over from the other.
Oh,
There will still be things where a regular digital computer, which will always be a simpler device, will do everything you need it to do. I mean, when I'm in my shop or I'm in my lab doing something and I need to calculate something like what a distance is or a size or how far to move a machine, I still use a little hand calculator because it's easier to use that than it is to go get my laptop and open up the calculator task and then run that thing. A little HP calculator does everything you need. So there will still be uses for a regular laptop. You will never use a quantum computer to type into Microsoft Word.
all right. That's good. Good to know. What
Yeah.
about other very computationally dense applications? I'm guessing medicine would be a real area where quantum computing could be helpful.
Yeah, again, where you're looking at many combinations. So you have data on many, many people and their symptoms, and you have, for example, image data. Imagine you have collections, a library of x-rays that have been taken of people. All that's data, and you have to sort through all that and make sense of all that. A quantum computer is going to be able to do that better because a conventional computer has to look pixel by pixel by pixel, right?
Right.
Imagine you could look at 60 megapixels at once and do something with it.
So imaging will be huge for this.
Imaging will be huge. Data visualization, where you have lots of data and you need to present it in some fashion, is going to be another major application.
What about televisions? Will it make our TVs better, sharper?
I don't know. That's probably more of a hardware issue in your TV, but
quantum TV.
Yeah, that'll be interesting.
I don't need. By the way, for the record, I don't need my TV to get any sharper. It looks fine. After an image gets too sharp, it looks weird. It starts to look like soap opera or something. It doesn't look like a movie anymore.
Yeah, very
What
true.
What about in defense?
Well, there are a couple of very important areas, and defense is one of the applications. Finance is another. But right now, all this information that's going back and forth between you and me is encrypted. So, we're working through StreamYard, and that URL at the top says HTTPS, right? It's a secure connection. It's not just HTTP, it's a secure connection.
Right,
and
okay.
Nobody can hack at least in theory, nobody can hack what we're doing. While we're talking here, all of a sudden, somebody else's face isn't going to show up and start talking over us or stealing our data or whatever, because we have a secure connection. And that's done using traditionally 128-bit encryption. That means each piece of information carries with it something that has 128 digital numbers going along with it that my computer and your computer have agreed to know about so that we can transmit information.
Yeah.
The thing is, 128 bits, that's a lot of combinations, right? To the 128th is a huge number. So it's very unlikely, not impossible, but very, very unlikely that somebody's going to guess that number. I mean, look at how hard it is to guess the Powerball. And that's only 5 numbers, right? Imagine if you had 128 of them, it'd be almost impossible to guess it. Here's the thing. A quantum computer is really good at taking collections of things and figuring out the most probable combination, right? So a quantum computer could undo encryption.
Which is good and bad. Bad for me, but good if we're trying to figure out some enemy's code.
Right. Or it has to end up being a lead-in to develop new ways of doing encrypting, right? When I'm going to make a bank deposit later by taking a picture of a check somebody sent me and send that to my bank. I want to make sure that only I know that and only the bank knows that, right? You don't want to send your financial information where all of a sudden somebody else knows that. So we're going to have to develop new encryption technologies. So as you're talking about, I mean, from whether it's military, whether it's finance, whether it's just video transmission, all of these things, everything that goes encrypted, quantum computers are going to have a big say about that, whether it's the risk to having it stolen or developing new methods of encrypting information so that you can send it from point A to point B without it being misinterpreted or stolen.
Further in defense, right now, you can shoot down a missile with a missile, but not every time you miss a lot. Will quantum computing make it easier to protect ourselves from attack from missiles and shoot down other missiles?
I don't know. I'm not quite sure how, all the different variables that are involved, whether the limitations are more the hardware and the difficulty of dealing with air currents and all the things that make it hard to do things in the real world, right? It's one thing to simulate it and say, well, if I follow this trajectory, these two things are going to hit each other. But then, a gust of wind and you miss, right?
Right.
I'm not sure where the limits are, but, every step forward should make things work better.
Any other applications that just are obvious that we haven't covered? Or are those the main ones?
I think those are certainly ones that people are looking at. But again, anytime you can look at very big systems, and another one is like materials. I mean, if you want to make a material, you have to simulate what all the atoms are going to go do in it. And those materials could be new things to do manufacturing. They could be new ways of doing circuitry. It could be ways of doing optical things. So this technology will help develop other technologies, right? Because right now you can't simulate how all the atoms behave in anything because there's too many variables. But a quantum computer is going to be able to do that.
Is quantum computer more fragile? Is it easier to interrupt? Is it more susceptible to, I don't know, humidity, environmental conditions, electronic pulses? Is it more vulnerable?
Oh yeah, well right now, of course, they're big laboratory instruments and they're very, very delicate. So that's what we're talking about when we talk about the errors and fault tolerances. It's very hard to keep these atoms in the same place at the same time doing what you need them to do. It's very hard to do that. And so yeah, they're very delicate at the moment.
And you mentioned they have to be very cold. Can you remind me why that is?
So temperature is a number we use that is connected to how fast particles are moving. So there's air in this room right now at about 70 degrees. And that tells you roughly how fast each of the atoms in the air are moving. If I raise the temperature of the room, if the room went up to 95 degrees, those particles are going to move faster. Well, if I want to keep them close together for a long time, we have to not have them moving or have them move very little. That means we have to make them very, very cold. And so you have to take all the air out around them. You can't have anything bouncing into them. So they're in vacuum chambers, and we have to lower the temperature so that they are moving very slowly so that they can talk to each other.
But you can't have 0 Kelvin or they would just stop and your machine would break.
Well, I mean, there's no way to reach absolute zero, but you can be very close to it. So these things work only a few degrees away from 0 Kelvin.
Wow. How fast do they go at that? Do they go, can you keep track of them?
Oh yeah. You keep track of them with lasers. Lasers are actually holding them in place.
Oh man. Well,
it's amazing what physics can do. It's wonderful stuff.
It sure is. And you're a great teacher. You explain these extremely difficult concepts in a way that even I and I think most people can understand. And that's why Doug is, I hope you all get to meet Doug someday. Doug lives up in New Hampshire. He's got his own observatory, builds his own telescopes, you're still doing the sessions where you go into classrooms, etc., and you can show people what's going on through your telescopes by way of cameras mounted on the telescopes. So you can, in real time, show them sunspots and stuff like that. Are you still doing that?
Oh, absolutely. Yeah, we do lots of programs like that. And I do lots of programs in person as well. Folks can, if you go to our website, which is mountainsofstars.org, there's a lot of information there. And I do programs all over the place. I'd be happy to come and visit groups if you put a group together and do some interesting things. There's a lot of great science that goes all the way from just understanding the universe to realizing how we're connected to it and maybe changing the way we do things because we understand where we fit in a whole lot better.
Okay. And of course, there's your Dark Skies project. And I think that is real important and really cool. Can you tell folks about that?
Yeah, so we work hard to try to improve lighting. It's not that we shouldn't have light, but we waste so much of it. And not only does that create health and energy and safety problems, but it means we don't see the stars. So people aren't connected to the universe because you just plain can't see it. But there are ways to do lighting much better. Lights that are shielded or only on when you need them, that have the right color and the right brightness. You have a much better environment to live in, and then those stars come back. It's really a very special thing. So again, there's a lot of information on that on our site. I'm on US and international commissions working on these
Right.
issues to try to make it better for everybody.
Any light that goes into the sky, unless it's a spotlight and you're looking for something, is completely wasted. Wasted light, wasted energy, and
Yep.
certain simple fixes like a shield on a reflector on the top of streetlights that reflects the light back down would make them more efficient and keep a lot of light out. The only light you get is it reflecting back off the pavement. When you're in an airplane, you can see these big circles of light, which is the area that they light on the pavement. But you could improve things a great deal. There are two really dark spots in the country, right? Only two left. Two darkness reservations, if you will.
There are a few places. Most are not very accessible, but there are several places you can go. Up here in New England, up in northern Maine, there's a large area, almost 100,000 acres, that's been protected. I led that effort as an international dark sky park in the Maine woods. So please come and visit that. It's a great place. We have telescopes. There are beautiful lodges, great places to do outdoor things. And then you see a really, really beautiful sky at night. There's a new dark sky reserve that was just awarded in Southwest Texas, out around the Big Bend area. And that's, again, one of the few areas you can go. Hard to get to, though, compared to getting up to Maine. So there are a few places, but please come up and enjoy our great spaces here.
One final question: how do you enforce the the dark skies? It's 100,000 acres is a lot of area to cover. Do people have to, I don't know, when you get a permit to have set up a light? Are there the light police, the light rangers? How does it work? I don't mean to joke about it, but
Yeah.
the reality of enforcing it must be difficult.
Well, these lands that we've protected up there, for the most part, are controlled by the Appalachian Mountain Club. And so within their facilities, their lodges and camps, all those lights are under control.
Oh,
There
good.
are no other buildings or features. I mean, there are some small camps, but they're off grid, that would affect that. Now, when you go to the surrounding towns, as we work from our park to what we call the reserve, the surrounding towns will have to both improve their lighting, but then actually put laws on the books, actual zoning
Good.
that says this is the lighting you can have and this is the lighting you can't have. And again, because this is generally beneficial, it's not like, oh, you can only watch these TV channels, you can't watch those. It's, oh, if you improve this, you will save money because you'll have less electric bills and your house will be safer and it'll be healthier. Kind of what's not to like. So it's helpful that way, but it is it's a challenge to try and get folks to do that.
Well, I cannot thank you enough for spending time with us. It's always wonderful. You're the best. Thank you, Doug Arion. And we'll definitely see you again in a month if I don't make it up there before that. So thank you very much. And folks, if you know people who dig science or people who like computers, why don't you share this episode of the broadcast that's talking about quantum computing? Thank you very much, Doug Arion.
Hey, thanks, Bradley. I love chatting with you. Looking forward to next month's discussion.
Okay, be well.